Thank you, thank you. It's a huge pleasure to be here, a big honor to be invited to speak to your school. I'm a huge admirer of this idea that you had to invite people from all around the world to come and talk here. It's a great way to make intellectual contact and academic contact, so big admiration for that. So today I thought I'd begin by just introducing a little bit myself and some of my interests. I'm currently at University of Victoria in Canada, so from far away. Oh, hello. Friends from Yaz. From far away, it looks like a dot, but where is the dot inside the country? We'll see. Well, as an undergraduate, I studied electrical engineering. And in the process of studying engineering, worked very hard learning a lot of tools for creative problem solving in the real world. That's something that engineers do. And along that path of learning all these engineering tools, I discovered mathematics. And it came kind of late in the game, but I really fell in love with mathematics because it's beautiful, it's pure, you can be sure whether you're right or not, you have a proof or you don't have a proof, and it's a beautiful subject. So I changed my area of interest and I did a PhD in mathematics. And then what happened was eventually they invented computer science. And computer science is a great subject because it spans this real-world application, creative problem solving that engineers do with the pure, beautiful things that mathematics do. So it's a kind of a natural bridge. So that appealed to me a lot. So here's a kind of academic timeline of my academic life. So here's electrical engineering, these years in here. And here's a mathematics. My life as a PhD student in mathematics at University of Wisconsin, studying discrete geometry, finite projective planes. So very combinatorial, very discrete, kind of geometric. And then I worked as a mathematician for a while, and the people in the math department said, oh, well, discrete geometry, combinatorics, they've invented this field called computer science. You should go away for a year and learn all about computer science and come back and help people in the math department with teaching computer science. So I did that in 1981-82. I spent a year visiting the computer science department at Cornell University to learn computer science. That was the original plan. And as I'll show you in a minute, something interesting happened with that plan to learn computer science. But then in 1983, on the basis of this computer science I learned here, I got a good fortune of being able to accept an academic position at McGill University in computer science. They just started a new department, had many people interested in studying computer science and no prof, so they had to make do with a mathematician who learned a little bit of computer science. And then in 2008 here, I moved to the University of Victoria. I changed my university. So all this is to say, why am I telling you this? My viewpoint is not pure computational geometry. I would say amongst us three speakers, it's Martin Loeffler, who is the pure computational geometer amongst us. And Helmut doesn't feel that he's a computational geometer, and I'm kind of a computational geometer, but not exactly. I have these other interests and viewpoints, as you'll see in my talks. So you'll see my interests as reflected in these talks are not, they don't look exactly like computational geometry. It's not right out of a computational geometry textbook. So this has influenced my taste. I like things that are at least potentially applicable, and I like things that are beautiful. And the bridge between the two of those aspects is something that appeals to me. So the world is going to be changing even faster for you than it has changed for those of us who are here talking to you today. So all I can suggest is stay curious, stay flexible, follow your interest, and expect to change what the problems are, what the technology is. In computer science, the problems that are interesting are very much technology-driven. When we have quantum computing, what's computational geometry problems going to look like then? You know, it's very technology-dependent what the problems are that are interesting. So this is kind of different than mathematics. All right, so next question, where is the University of Victoria? Well, it's on an island in the Pacific Ocean. The island is called Vancouver Island. It's a huge island. It takes maybe 6 hours to drive from one end to the other. And it happens to be close by a city called Vancouver, but they're not, it's not like Utrecht being the center of Utrecht. It's Victoria here, and then take a ferry and you get over to Vancouver, the city on the west coast of Canada. It's close to Seattle in the United States, the northwest area of Seattle. This also is the United States. The border between US and Canada runs something like that. So that's where I'm located now. So algorithmic robotics. So back to that year, visiting Cornell to learn computer science. I was sitting in on some courses, variety of courses, and one of the courses I was sitting in on was a course in algorithm design taught by John Hopcroft, and he said, "Sue, why are you sitting on all these courses? The way to learn computer science is just do it. Forget learning anything about it. Just dive in and do it, and let's do research together." Okay, that's the way to learn. So that's what happened. So all to say that my knowledge of computer science has been learned along the path, not as a student studying exactly what's computer science. So the topic that John was interested in at that time was theoretical robotics. And there was a series of papers at that time by Schwartz and Scherer called Piano Movers 1, 2, 3. I forgot how high they got. Piano Movers 6, maybe. They were interested in motion planning problems where you had some big bulky object and you wanted to get it through the door. There were papers on moving a chair out the door, all kinds of moving this kind of object past some obstacles. And these mathematicians started to look at those problems in a more precise mathematical way. And John said, "Here, read this 75-page manuscript and let's talk about it." So I looked at the 75-page manuscript. Oh my goodness, this is going to take a long time to master this. So why don't we just ask a simple question? So John was about to start a lecture one day, and I asked him a question, and he liked the question, and so we got interested in the subject of reconfiguring chains of links, which is what I'm going to talk to you about today. So the objects we're going to study in 2D or 3D, you can study these in any dimension, actually, and I'll mention that very briefly. They're sequences or chains of links. We can call them links, rods. They have positive integer links, let's say. So they're not flexible. They just are rigid rods. And they're free to turn about their endpoints. It's hard to do that. So they can turn 360 degrees around there. So you can think of it as a kind of 2.5-dimensional figure looking down from the top. So we see some edges that are allowed to cross. You could think of it also as specifying the distances between points, and these edges are just there to suggest a distance constraint that has to be maintained. So here we have 4 links. Maybe they're allowed to cross. Here we have a polygon, a cycle of links that's crossing. Some notation here for future slides. A0 is going to be the endpoint of the chain, and then we'll have A1 up to AN, and we'll denote the link that joins AI minus 1 to AI as having length L sub I. So L sub I, that's the distance from AI minus 1 to AI in these pictures. Li is the length of this rod here between AI minus 1 and AI. Here's the chain, non-crossing polygon. Well, later on, we're going to get interested in applying the rule that the links are not allowed to cross. So we'll consider both kinds of problems. So what I hope to do this morning is to convince you that these very simple objects have interesting properties and surprising behavior. At this point, they have quite a history, and they have connections to many fields because they can serve as models, for example, for molecules. There are lots of chain reconfiguration problems that are easy to solve, as we'll see. And there's some that we still don't know the answers to. And there's some we know are these so-called intractable problems. So it's interesting to me that there's such a huge variety of behavior and questions you can ask about such a simple object. To me, that's a kind of a beautiful problem when there's something that's simple that you can understand, and yet when you study it, this complex behavior emerges. So ruler folding, I'm sentimental about this problem because it's the first problem I ever asked in computer science. It was the kind of the beginning of my life as a computer science person. And when John was beginning his lecture one day, I said, and part of this was just to defend against having to read that 75-page manuscript. So what happens if we have a ruler, a carpenter's ruler, let's call it, a chain of links, and we're given the lengths here, and we're given some maximum folding length, positive integer, and we'd like to know, yes or no, can we fold that chain into that length? And John started giving us lecture on some totally different subject, and at the end of the lecture he says, I like that question. And he said, I think it's one of these hard problems. So NP-complete, at that time, did I know what NP-complete was? I don't know, but I learned rapidly after that. So we were able to show, so by the way, here, the links don't have any thickness. This is an idealized picture. These things can fold back and forth on top of one another. They're not obliged to entirely fill out the case, but they certainly can't fold longer than the case. That's against our rule here. So we were able to show that this problem, this simple problem, yes or no, can you fold these links so they fit into a specified length, line segment of length k, that's a hard problem. That's one of these NP-complete problems. That simple problem is hard. And one shows that by reduction from set partition problem. But on the other hand, if you bound the length of the longest link, then you get a linear time algorithm for solving this problem. So it's interesting that bounding the length of the link, which seems like a reasonable thing to do, suddenly gives you a linear time solution, a simple linear time solution, whereas the chain in the question is powerful enough to encode the set partition problem. So, interesting. So let's see how that goes. I assume most of you are thoroughly familiar with NP-completeness. You're computer science students. This is not new. But I'd like to just go through how this reduction works. So set partition, as you'll recall, says you're given a collection of positive integer weights. You can have repetitions, that's fine. And the question is, yes or no, can you divide the weights into two separate piles, S1 and S2, so that the sum of the weights is the same? So this is like a balance on the playground, and you want to put some of the kids on one side and some on the other, and you want it to balance. Can you do that? So here's how to encode that problem into a ruler folding problem. Here's a very special kind of ruler for which the answer to this question is the same as the answer to this question. you make a very long first link and last link. The length is going to be twice the sum of all the weights in your set partition problem. And then you make a very long, but only half as very long, second link and next to last link, whose length is the sum of the weights. And then these other links are just going to copy those weights. Their lengths are going to be given by those weights up there. So maybe this is W1, W2, W3, and so forth. That's the ruler. That's what we're going to try to fold. What's going to be the budget? We're going to we have to make the budget K. What works out for encoding the set partition problem is to make the folding length, the desired folding length, twice the sum of the weights. So the desired folding length is going to be just long enough to exactly fit those two longest links. That's what we have to do. Yes or no, can we do that? So very specialized ruler, having such a long link at first and having this folding length that's just exactly enough to contain the longest link. Very special. Okay, so we're taking set partition and making it look like a very special case of ruler folding. So proof sketch, if your set can be partitioned into equal parts, S1 and S2, then what we can do to get the folding of the ruler is to aim these links here according to whether the corresponding weight was in the left set or the right set. Because notice that this long link just fits in the case, and so this joint has to fold back, so this is going to be at the midpoint of the case. And similarly here, no matter which way around we put this link in the case, this point is also going to be at the midpoint. So these 2 points are on top of one another, if we can put that ruler into the case. So if we have a partition up here that balances, if we see the first link was in the right part, we'll aim that link, the first link of the little guys, we'll aim that to the right. If the second was in the right, there. If it was in the left side, we aim it back to the left, and so forth. And because those weights balance, that's going to mean that the total distance we move to the right here, these links of these paths moving to the right, is going to exactly equal the distance that we move to the left with these leftward aiming links. And these 2 points will match up, and we will have put the ruler in the case. So from a solution to set partition, we can read off a way to fold the ruler. So if the answer to this is yes, the answer to this is yes. But we need to see the other way around. If we can fold this, does that mean that the weights balance? And it's essentially the same idea. Because these two points here have got to lie on top of each other by the way we design the ruler, we know that the distance we went to the right has got to equal the distance we went to the left, and we can just read off from this how to put the weights in the pile so that they balance. So it's an encoding of set partition into a very special case of ruler folding. Okay, so a consequence of that for motion planning is that it's not going to be an easy problem to decide how to move around an object that has many degrees of freedom in a simple environment like a room with a narrow passageway in it. So here we have n degrees of freedom here, the angles that we choose for these rods here. But if we make this gap narrow enough and we make this doorway here roughly k, and we're not going to be able to reorient a link once we put it in this tunnel. So that means if we're going to get this object from this side of the room to the other side of the room, we've basically got to fold it up into length at most k, in order to get it around through the tunnel and out the other side. It was just a simple demonstration that motion planning problems, when you have a lot of degrees of freedom, are going to be hard problems, even if you're moving something very simple. However, if we bound the length of the longest link to m, then we're going to see we can solve this problem in linear time. How does that work? So let's let m be the longest link. And we want to observe, to get our fast solution, that every ruler folds into length twice the maximum link length. Guaranteed. And why is that? Well, you can just be greedy. You can start over at one side of your case, say 0, and you take a step of length L1, take another step of length L2, and so forth until you reach the first length that doesn't fit. And then turn around. Now, if it didn't fit, that means you must be past the halfway part, right? Because this is the length of the longest link. If you were back here, you could keep going. So you must be over here someplace, and that means when you turn around, it's going to fit the other way. So you keep coming back this way until you come to a link that doesn't fit, and you switch directions. So that simple greedy technique is always going to fold your ruler into this length 2m or less. Nothing says you have to use that entire amount, but for sure, you never need more than that for any ruler. Okay, so what can we do with that? We're going to solve this problem with dynamic programming. And I have to say, one reason I'm fond of this problem is not just nostalgia, and because it exhibits interesting properties, but also it illustrates a lot of elementary ideas from first course in algorithms. It introduces a lot of concepts from theoretical computer science in a very simple way, and it's a wonderful source of problems for students and still some open problems. So let's see how we solve this problem with dynamic programming. And it's going to be a kind of strange looking dynamic programming, because at the time I had no idea what dynamic programming was, so these tables somehow don't look right in terms of what you read in a textbook, but it's the same idea. We're going to make a series of tables, and the first table is really going to answer for us the question, yes or no, can you fold the ruler into length m, the longest link? And if the answer is no, then we're going to build another table and ask, can you fold the ruler into length m plus 1? So we're going to build a sequence of tables like that. So in fact, we're going to find the minimum folding length of the ruler. And we know this process is going to stop, right? Because we've just seen that no ruler ever needs more than twice the maximum link length. So we know we're only going to have to build roughly m tables, and we'll be done. Maybe we'll be lucky and the first table works, but in the worst case, roughly m tables. And you can figure out, would m minus 1 tables be enough in the worst case, but that's a detail. Okay, so what we're going to do is make the columns, we're going to have the columns of our table be indexed from 0 up to m, if we're starting with m. Here I have 2m, but m is what I meant there. So position j, we're going to have integer position 0, 1, j, up to m, and eventually up to 2m if we need it. And the rows are going to correspond to initial segments of our ruler. So row 0 is going to correspond to just the point, A0. Row 1 is going to correspond to A0, A1, and we're going to cut off the rest of the ruler. Row I is going to correspond to the ruler terminated at AI, and we throw off the rest of the links. And the question we're going to ask when we fill out this table is the following. Yes or no. So I'm going to put a check mark in row I, column J of the table, if it's possible to fold up the initial part of the ruler ending in joint AI in such a way that it fits in the case and AI is positioned at J. Yes or no? Can I do that? So let's see what happens when we start doing that. Here's our position on the x-axis up at the top. J going from 0 up to M for the first table. And look at row 0. Check, check, check. I can take a point, A0, that first joint with the rest of the ruler thrown away. I can put it at position 0. I can put it at position 1. I can put it anywhere. So no problem placing a point. I get checks in the entire first row, or 0th row, we're calling it. Now notice how I can process checks from one row to the next. If I have a check here at position J, then, well, imagine I'm wanting to know where I can place joint HA plus 1. Well, HA had to be somewhere. So where could it be? Let's say AJ was at this check, then AJ plus 1 has to be Li plus 1 away. So it could be either to the right or to the left. So each check in one row is going to generate at most 2 checks in the next row. Why at most? Well, depending on where this check is in row I, and depending on this length, Li plus 1, maybe this goes outside the bounds. Maybe this, I don't get any check here. And maybe this goes outside the bounds over here. So I have a bunch of checks in one row, and I just process them all with this simple arithmetic. I verify whether we go outside to the left or outside to the right, and if I don't, I put checks in the corresponding places. So just in constant time per table entry, I'm putting in all these checks. So what happens if I get stuck? What happens if I'm processing a row and I don't get any checks in the next row? What does that mean? There's no way I can fold up that ruler into the folding length 0 up to M. I would have to place all the initial segments of the ruler, and then if I get to some place where there's no place to put the next joint, I'm stuck. I can't do it. How do I turn, once I've filled out the table, how do I determine whether it is possible to fold up the ruler? How does that manifest itself in the table? There's a check in the nth row. Is it unique? Not necessarily. I might have lots of checks here. There might be many checks. There might be no checks. But if there's a way to fold the ruler, then there's a way to fold all the initial segments of the ruler right up through the last link. So I'll get a check there. So how much time does it take me to fill out this table? Well, I have n links. M is just some constant, 100 links in my ruler, say. Oh, sorry, not links, length, m centimeters in my ruler, say. So it's just some constant. So in linear time, I've completed this table, and I know whether m is good enough or I need to go to the next table. So if I need to go to the next table, I just do that. And I know that I'm going to have to go to the next table in most m times. So I have a linear time algorithm for answering this question when the maximum link is bounded by some number m. Okay, so that says as much about asymptotic notation, perhaps, but yeah. So linear time, you can solve this problem if you bound the length of the longest link. Okay, so something else we did there that year, 1981-82, was look at the Poissonnier device, which is a mechanism where one point draws exactly a straight line. You move the device around, and you have a point on it. It's a linkage with 7 links, and one point moves exactly on a straight line. So we designed a mechanical computer that used Poissonnier devices to make bit registers. So when a point was at the top of its travel along this line, we thought of that as a 0, and at the bottom that's a 1. So we made a mechanical computer, and we could say, it kind of modeled a Turing machine, so we could say, if a point moves to a certain place, you can do that if and only if this Turing machine accepts its input. So we knew that the problem could be very hard indeed, that question of can you move your device so that a point reaches a particular place in space. So we knew that reconfiguration problems for moving linkages in the plane are p-space hard, and then that was later shown to be p-space complete. So here's some reconfiguration problems that we showed were easy. We said, okay, let's put this linkage inside a container and see how that influences the difficulty of moving around. So instead of just trying to fold it up, let's move it around inside of a disk. We were kind of thinking of a robot arm situation, idealized. So we have this red point P. We're trying to touch it with joint AN, the last joint of the ruler. And the star, that's a thumbtack. We thumbtacked down the beginning of the linkage. And we just want to know, can you touch that point P? And it turns out there's a polynomial time algorithm for doing that. And Kantabutra and Kosaraju later came around and showed that there's a better, faster algorithm than the one we had. And then they started saying, well, why circles? Why not squares? So they got interested in moving linkages around in squares. And they asked a similar kind of question. Can you touch a point P? And there they could answer the question with a nice algorithm, provided that the longest link, all the links had length at most the side of the square. And one of Mohammed's students was asking me, oh yeah, well, suppose this condition doesn't hold, then what can you say? So there's still plenty to talk about there. Another thing we did, so this is now with Peter Eads, what happens if you try to move around a linkage inside an angle? So just a wedge. And there, what we were trying to do was touch a point or just to pull the linkage out straight, put it out on a straight line aimed away from the corner. And we found that if the wedge was bigger than 90 degrees, then that was an easy problem to solve. But if the wedge were acute, less than 90 degrees, we couldn't figure out the answer. We struggled with it. We couldn't figure out how to solve that problem. Exactly 90 degrees, I don't remember which side that lies on, the easy side or the hard side. Probably depends on your model for what you allow. But yeah, if it's an acute wedge, then can you pull that out straight from this pin-down point? And no. Then I had a student, Pei, who got interested in these problems, and he said, all right, let's generalize squares to convex polygons, not necessarily regular ones. And he looked at what he called convex obtuse polygons, so each angle was going to be at least 90 degrees. And he found, again, algorithms when the longest link was less than the smallest side length. He could solve those kinds of problems. Can you touch P with AN? Can you design an algorithm to move that length around to touch P? So one of those conditions needed for the convex obtuse polygons, well, notice that you can have a link that gets stuck. If you're trying to move it this way, it's on the diagonal. You can't move it. If the polygon's not convex, then you're trying to move this link around the boundary by keeping the endpoints on the boundary, then the link is going to lie outside the polygon. And in a situation like this, if you're trying to move this link so that the endpoints track the boundary, then you're going to get stuck here because this distance here is not long enough to let your link swing under the other endpoint and reorient itself. So basically the idea there was kind of to throw the links, get the links out onto the boundary, store the links on the boundary, store the endpoints on the boundary, and then try to design a way to move the links around the boundary. So that's why those conditions were needed. Some ideas that came up here. So notice, if you try to model this problem, it's got end joints. If you try to model this problem in configuration space, you're going to get a very high-dimensional configuration space. If you say you got to specify the angle at each one of those joints. So it's a question of trying to say something interesting for a very special case of a reconfiguration problem where you have so many degrees of freedom. So notice that links can have a kind of orientation with respect to the boundary. So in this case over here on the right, you can't reorient the middle link because the two adjacent links are so long, they don't allow that middle link to get very far away from the boundary of the circle. So you don't have the chance to take that middle link and, say, put it on a diagonal and flip it around and reorient it. Those chopsticks are forcing the two middle joints to be close to the boundary of the circle. So that's constraining what you can do. So that's a useful idea. We tried a notion of a canonical configuration. So another idea is try to move your object to some so-called canonical configuration, some special configuration, everything that's straightened out, for example. And then use that as an intermediate configuration. If you can move everything to a canonical configuration, then from there you can play the movie backward to get to the configuration of the chain that you like. So that's another useful tool. So here's a curious phenomenon. So about this time, Mark van Creveld came to do a postdoc at McGill. You'll recognize Mark van Creveld's name from the famous 3 Marks in Ottfried's geometry book. So this was the guy, and he says, "Do you have a problem for me?" And I said, "Well, yeah, I was just talking with Peter Eads, and we got stuck on this problem, excuse me, with a wedge less than 9 degrees. So as a warm-up, can you solve that problem?" What can you say? And Mark went away and came back sometime later and said, "Well, gosh, I couldn't solve that problem, so I contacted my friend Jack Snoeink, and together we couldn't solve it, but we changed the problem." So we changed the problem. And the problem they proposed was this. Let's say you're moving around a chain of links inside an equilateral triangle. So forget it. They thought this would be appealing because it's an acute angle that we're dealing with here. We know acute angles somehow present some difficulties. But they were willing to say, let's make all the links have the same length. So here's the length. They all have the same length. It can be as many of these links as you like, but they all have the same length. And let's study what happens as this length of each link changes from 0 to 1. What's going to happen? And the following, I think, astounding behavior came out. So when all the links are very, very tiny, it doesn't matter how many links you have, they can rotate around each other, you can always move from any configuration to any other configuration. So you get yes. So on this line from 0 to 1, as the length changes from 0 to 1, I'm going to look for where I get this transition. From yes, I can always reconfigure any chain initial configuration to any desired final configuration, to no, I can't always do it. Because look, here, if I just have two links, and they both have length 1, or roughly length 1, if I put that in like this into the triangle, there's no way I can squeeze them shut. So definitely when L gets close to 1, if each link has length approximately 1, I'm not going to be able to do it. So what we wanted to know is, where is this transition? And what turned out to be the case is the answer alternates. For a while you can always do it. For a while, sometimes you can do it and sometimes you can't. It depends on what the configuration is. And then all of a sudden you can always do it again. So this is really quite surprising, I think. And these numbers here, approximately 0.483, it's this expression, and it comes from a configuration that looks like this. You have a link, it almost reaches the midpoint, and then it goes across to just above the midpoint, and then straight down. So you can't move this way. There's not enough room to get it under. So that happens at 0.483, and then here's connecting the midpoint to the midpoint. The corner to the midpoint, to the midpoint, to the corner. That's 0.5, and then this is square root 3 over 2. So then Pei found some more examples of this for regular n-gons, more examples of this strange alternating behavior for when you can always do it and when you can't always do it. And intuitively, I think you can imagine that why you get another yes here is that your links are long enough that you can't fit them in badly. There's no way to fit them in an awkward way that keeps you from reconfiguring. So it's a strange thing. All right, so let's take a look at closed chains with no obstacles. So now instead of having an open chain, we have a closed chain, and we want to reconfigure it. And my former student Bill Linhart and I, we got interested in one we called it turning a polygon inside out. So you have a chain of links in the plane, and you'd like to just reorient it, turn it inside out. So let's say the joints are numbered, A0, A1, and if we go around from A0 to A1 to A2, we might be turning in a clockwise direction, or we might be turning in a counterclockwise direction. And we notice if we just have 3 links, it's a triangle, and for sure this configuration can't reach this configuration, and unless we pick the triangle out of the plane and put it back down, which is not allowed. So no, you can't always do it. But it turns out triangles aren't the only thing that could go wrong, because after all, I could have 3 very long links, and I could attach them with many, many links that are very, very short. And so this ensemble has many links in it, and yet, 204 links. But essentially, it behaves like a triangle. So when can we take the chain and make it convex, and then as a kind of canonical configuration, and then having done that, when can we turn it inside out? That was the kind of question we started looking at. So what we found was this. For closed chains and 2D, there's exactly one equivalence class of configuration. So equivalence class, 2 configurations are in the same equivalence class if you can move from one to the other without picking anything up from the plane. So you get exactly one equivalence class if and only if the second longest link plus the third longest link is at most half the perimeter. The second plus third is at most half the perimeter. Is that the case for the triangle? the second plus the third length? Is it at most half the perimeter? No. So for the triangle, as we would expect, this condition is violated. It's a necessary and sufficient condition, so you're not going to get one configuration class. And we've seen that. You get the mirror image. And in fact, we were able to show that if the condition doesn't hold, then in fact you get exactly two equivalence classes, and each configuration in one class is just the mirror image of a corresponding configuration in the other. And then in 3 dimensions and higher, you get exactly one equivalence class of configurations of these chains. You don't have this mirror image thing. There's not enough room in the plane. But in 3 dimensions and higher, you can. So here's the proof technique. It's a very simple proof technique to get these results. Notice that if we define an elbow to be 3 consecutive joints, and we fix the position of one of them down, we can think of the middle joint as kind of an elbow, and the next joint is kind of a hand. And if we folded that middle elbow joint, then A2 would be able to draw this inner circle here. It's like polar coordinates, right? Just these 2 little joints. And if I straighten the middle joint, A1, then A2 can draw the outer circle. And if I draw any curve there in the donut, then this end, A2, can track that curve by just how we adjust the angle at A0 and how we adjust the angle at A1. It's just a question of getting the right distance between A2 and A0. So we can draw any curve we like. Oh, that's pretty good. Now, what if we go 2 more steps away and think of these 2 joints as shoulders that we pen down. So here's going to be one elbow with a hand A2. Here's going to be another elbow with a hand A2. Can those 2 elbows cooperate to move this point? So if you notice that if you draw a line through these 2 fixed points, then if you move that hand, you're trying to cooperate to move upward, perpendicular to the line, this point will be moving away from this shoulder and also away from this shoulder. It's moving away from the line. It's moving away from both these points. So if you go far enough, what's going to happen? One of the other elbows is going to straighten. This point is getting farther away, so this joint's got to be opening and this joint's got to be opening. And so one of them will eventually straighten. Then you can apply induction. And notice the same idea works in any dimension. So you can just take your length and your space and go 4, draw a line, go in the perpendicular direction, and you'll straighten the link. So some questions arose from this, and that is, what happens if we don't allow the links to cross through one another? So in 3D, not 2.5D, we can do things like tie a knot in our shoelaces and then attach very long knitting needles to the shoelaces, and there's not going to be enough room to pull these long links through this little knot we've tied there. So originally Bill and I thought, well, maybe we solve the 3D problem by just projecting things onto the plane and maybe looking at the shadows, and that'll tell us how to move things around in 3D. But no, we just came to discover a whole collection of new interesting problems. So when can a simple chain, so non-crossing chain, be straightened in 3D? We still don't know the answer to that. We don't know the complexity of that. When can a simple chain be straightened in 2D? This is where we noticed the shadows weren't going to help us out because we couldn't answer this question in 2D either. And when can a simple closed chain be made convex in 2D? So those were questions that we thought were very intriguing at the day. And we went around telling a lot of people, can you solve this problem? You know, it was bothering us walking down the street that we don't know whether you can straighten a chain of links in 2D. I mean, that's an amazing thing not to know the answer to. Then my colleague Gottfried Toussaint said, with star-shaped polygons. Gottfried was very interested in star-shaped polygons. He said, suppose you have a star-shaped linkage. Can you make that convex? So star-shaped, we studied star-shaped polygons for a while. So that's a polygon that has a point or a region in it, such that any point in that region can see the entire floor plan of the polygon. And colleague at a workshop, Heiko Schroeder, suggested, he's an engineer, right? He wasn't a computational geometer, so he suggested the obvious thing of blow it up. So make lines that extend through every other ones of these points in the star, never mind even or odd here, and then just have them move at constant speed. Does that do it? So eventually, years later, at a workshop, we were able to prove that yes, you can make that idea. You can make that idea work. You can convexify star-shaped polygons with this idea of moving points along at constant speed. And then we had a variety of other results at that same workshop. And you'll notice Eric Domain, who was, 16 years old at the time or something like that, he came along with his dad, Marty Domain, and we started playing around with these linkage reconfiguration problems. And we got results like, well, you can pull them up, you can take a chain, pull it up into a vertical line in 3D. You can make tree-like linkages that lock if you can find them to the plane. Got a number of interesting results about linkages. Pocket flipping, that's another thing. The trees that lock, here's an example. So here's a tree, and it's got degree 5 there. And we were able to prove with a lot of trigonometry, not just looking at it, but actually working out the details, that you cannot straighten this out. So straighten it out would mean you have this root, say, and then you have all these paths, and they're essentially lying along the x-axis. You cannot straighten it out. You're pretty much stuck with a little bit of uncertain wiggling around here with this configuration. If your initial configuration is like that. And we later used this gadget for, so by the way, that means you can have lots of configuration classes of a tree-like linkage. Because you could have a tree that has some bits like this that are essentially in that configuration and some parts that are straightened out and some parts that are like that. So you can get exponentially many configurations and a tree-like linkage. So here's a fascinating example that came from Cantarella and Johnson. And they said, you can have cycles of links in 3D that are not knotted. There's no interlinking here. And yet you can't move this out into a convexified position. If you could bend the wire, sure, you could do that. But if you're not allowed to bend the wire, you just have this possibility of moving these joints, that's it. You're stuck in that kind of configuration. You can't make that convex. So then along comes Connolly, Domain, and Rota. So Eric was giving a talk at a conference about some of our results, and Bob Connolly was there. He's a geometer who likes to blow things up, likes to talk about expansive motions. And Gunter Rota, who's good at modeling with linear programming, and they said, maybe we can model this as a linear programming problem where we ask that joints have got to get farther away from one another or stay exactly the same length if their endpoints are the same length. And they were able to get that to work. With an expansive motion, they could prove finally the answer to the question of whether you can straighten every chain in the plane. Yes, you can. And cycles without crossing. In cycles, you can turn every cycle into a convex position. And then Ileana Strinu, who was also at that same workshop we had, she gave independently a totally different approach, a kind of mechanical combinatorial proof. Her approach was to add bars in here until she only had 1 degree of freedom and then move that new linkage structure until some joints straightened. So very, very different approach from linear programming model, but she got that to work too. So what about folding other things? There are all kinds of things you can imagine folding 2D structures in 3D long hinges. What are the relations to origami? You might want to avoid self-intersections if the materials aren't flexible. There's a book that came out by Eric Domaina and Joseph O'Rourke, Cambridge University Press 2007, called Geometric Folding Algorithms, Linkages, Origami, and Polyhedra. It's a beautiful book, beautiful pictures, and it covers a lot of the topics I've been mentioning here and more. Later on, we used some of those locked trees to help us design a piece-based hardness result that you can't, the complexity of reconfiguring a tree in either 2D or 3D is a hard problem. So that's different from saying when can you straighten a tree that's a very special case, just a chain of links. So we don't know the complexity of that. We just know the complexity of the more general problem that it's hard to reconfigure a tree. If the tree is a chain of links, we still don't have any idea. What if the chain of links all have the same length, length 1 for each one of the chains? No idea, no idea. I kind of think if the chains have the same length, there's got to be some critical configuration that just says, no, you can't straighten it anymore. So in conclusion, some open problems that we've just mentioned here. Get reconfiguration results, complexity, algorithm results for moving around chains and triangles, whether or not they're simple or crossing chains. Acute wedges, we still don't know. Chains in 3D, when they can be straightened. I think this is a very interesting problem. Non-crossing chains in the presence of obstacles. So you can have all kinds of obstacles in your workspace, not just circles or convex obtuse polygons. How hard is it to move around a chain of links and obstacles? Chain straightening when you specify some simple motion, like a line tracking motion, just a simple moving of a couple of elbows. Can we straighten chains with some simple to carry out motions rather than linear programming or putting in bars? Chain motions that respect tolerances, so don't allow the links to get too close to one another. Tree-like linkages in 2 and 3D. And graph-like linkages. So there's lots and lots of interesting problems to look at here. And we're still just talking about links, not about cubes, not about flaps, not about panels. There's so many interesting problems to look at about reconfiguration of these objects that have a simple combinatorial relationship to one another that you want to preserve. So thank you very much. Appreciate your interest.